Thank you, Steve. Thank you for the invitation to talk at the workshop. Been enjoying the talk so far. I'll be talking about work that has been done during my postdoc at KTP, but then actually in a couple of weeks, I'll be joining the physics department at the Technion in Israel. So I'd like to tell you about basically matrix product state based methods applied to understanding dynamics of quasiparticles in magnetic systems. And in particular, I'd like to discuss kind of signatures of interactions between quasiparticles. But let me start from a bit of a more general introduction. So quasiparticles are really a basic notion of many-body physics. There's fundamental excitations above a many-body ground state. And we call something a quasiparticle if it essentially behaves like a particle. So when, in particular, it's a long-lived excitation. Okay, and then this famous caricature by from Maddox's book, he compares this notion of quasiparticles to a quasi-horse, which is when the horse is galloping, he's surrounded by a cloud of dust and behaves like a single entity. So in a similar way, a quasiparticle is kind of a collective excitation, which is a single excitation, a well-defined excitation. Okay. So I'll be talking about quasiparticles in magnetic systems, and by this I mean systems in which electrons are immobile, so they're pinned to the lattice, and then we can basically discuss systems of localized spins. Now, such systems very often order, and the exact nature of the ordering when they're cooled down to low temperatures depends on the exact interactions between the spins. Okay, this can be ferromagnetic materials when all the spins are aligned, or antiferromagnets when neighboring spins are antiparallel. Okay. Now, the basic quasiparticles in such systems indeed occur when the ground state of the system is ordered. So, for example, in a ferromagnet, we can think of flipping a single spin, and now this spin can kind of propagate around and therefore behaves like a particle. We call such a particle a magnon, basically, and we can create by considering superpositions of such localized flipped spins, we can create an excitation with well-defined energy and momentum, as you can see on the plot on the right. Okay. So we can also have more exotic quasiparticles in magnetic systems, or at least we hope we do. So kind of continuing Maddox's analogy, we would then think of fractionalized quasi-horses. And even though some evidence for existence of fractionalized horses have been proposed in the past a while back, we hope to find kind of better evidence for the existence of fractionalized quasiparticles in real systems. Okay, so fractionalized quasiparticles are basically quasiparticles that carry fractional quantum numbers. One of the famous examples is probably the fractional excitations in fractional quantum Hall effect, where the excitations carry electric charge, which is a fraction of the electronic charge, for example, 1/3 or 1/5. Okay. Now, in magnetic systems, fractionalized excitations can also occur when the ground state is essentially a spin liquid phase, when the ground state is not ordered. So this situations are pretty rare, of course, and we do not know if they actually exist in real materials. But one nice thing is that actually in one-dimensional systems, such fractionalized excitations occur pretty naturally. So for example, if you think of an antiferromagnetic Ising chain, which is kind of the extreme anisotropic limit of the system I'll consider in the rest of the talk, then we can see that, if the ground state is antiferromagnetically ordered, then by flipping a single spin, we're creating a spin 1 excitation, right? If we're thinking of spin 1/2 chain, we flipped a spin. By flipping a spin, we went from a spin -1/2 to +1/2, creating spin 1 excitation. Now, this in fact created two domain walls that can now propagate freely, and we can see that each domain wall carries a fractionalized excitation with an effective spin of 1/2. So we can think of this as what would typically be called a spinon. So it's a fraction of the magnetic excitation. Now, how do we probe quasiparticles in magnetic systems? Some of the most common probe for quasiparticles in magnetic systems is by looking at the dynamical spin susceptibility. So this is basically just the Fourier transform of the time-resolved spin-spin correlations. Okay, and this is exactly the quantity that is measured in inelastic neutron scattering experiments, so it's accessible experimentally. When we just scatter a neutron of a magnetic sample, and that way creating a magnon with some well-defined momentum and energy. So when the quasiparticles in the system are indeed magnons, so just flipped spins, what we'll see in this response is just a sharp peak, as you can see here, for example. While if the low energy excitations are fractionalized excitations like a spinon, so you'll see that this magnon will have to split into two particles, and then the spinons will show up in the response as a two-particle continuum. Okay, so there is no longer a sharp peak, but rather a continuum of excitations. And this has indeed been observed experimentally in a number of quasi-one-dimensional materials. Now, let me address how can we probe dynamical stability numerically. Okay. This will be the main quantity of interest in the rest of my talk. So if you're interested in understanding the low energy or ground state properties of the system, we can think of probing the system at zero temperature. Okay, and then basically when we're looking at the dynamical correlations, we're calculating the time-resolved correlations in the ground state. Okay, so this expectation is taken in the ground state, and of course we know that for low-dimensional systems, we can obtain the ground state very effectively using DMRG. Now, to calculate the time-resolved correlations, we know that if we use the Heisenberg representation of the operators, this amounts to eventually just time evolving a quench state. So we apply some S minus on the ground state and then time evolve the state, and that way we can calculate these correlations. Okay, and just to note. So the results for the dynamical correlations I'll show you later in the talk were obtained using the iTensor library. Okay, so in the rest of the talk, I'd like to kind of address predominantly the structure of the dynamical correlations, just in a very simple scenario of an antiferromagnetic spin 1/2 chain in presence of magnetic field. Okay, and I'd like to kind of address two regimes. One, first of the regime of low magnetization. So in this case, the low energy quasiparticles in the system are fractionalized spinons. And I'll show you that the dynamical correlations actually feature some signatures of interactions between these fractionalized quasiparticles. Now, in the regime of high magnetization, when the quasiparticles are just simple spin flips or magnons, I'll show you that interactions between the magnons also leave a signature in the correlations in the form of related to a formation of a bound state of these magnons. Okay, and this is work that was done in collaboration with Leon Balance from KTP and Oleg Star from the University of Utah. Then at the end of my talk, I'll mention just a few very preliminary results on understanding the structure of dynamical correlations in the high magnetization regime in higher dimensional systems. Okay, so let me start with a spin 1/2 antiferromagnetic chain. So I'll be considering just a spin 1/2 chain with both nearest neighbor antiferromagnetic interactions and the second neighbor interaction J2. And of course, the phase diagram for this model is very well known. We know that for vanishing J2, this model is integrable and system is exactly solvable by beta ansatz. And we know that the system is gapless. While as we increase J2, the system undergoes a phase transition into a dimorphist phase. And for J2 over J1 of exactly 1/2, this is what's known as a Majumdar-Gauss point, when we can think of the ground state as just a product of singlets on every other bond. Okay. Now the point of the transition between these two phases can be obtained numerically. But in the rest of the talk, I'll kind of address this gapless regime. Okay. So the low energy description of this gapless phase is also very well known. Basically, it can be understood as just half-filled band of this fractionalized fermionic spinons. Okay. So the spinons are related to the original spin operators by, or we can relate this by rewriting the spins in terms of currents of right and left moving spinons. And the currents are simply the densities of this spinons. Okay. So the low energy effective Hamiltonian would be just an Hamiltonian of those free left and right moving spinons. But then the most relevant perturbation to that would be a density-density interactions between the left and right moving spinons. Okay. So to understand kind of the fate of the system, we need to understand what this interaction does. And for that, we can perform our recoupling RG, for example. And what one finds is that kind of the fate of the system depends on the sign of this interaction G. So when G is positive, this interaction is marginally irrelevant. And the system remains gapless. Okay, so as we perform the RG, G flows to 0 and the system remains essentially non-interacting. While if G is negative, the system flows to strong coupling and the ground state of the system is gapped. Okay? So now relating this this picture back to the microscopic parameters, we understand that this interaction strength G is basically set by the Baire value of this interaction G is set by the macroscopic parameters G2 over G1. Okay? And in particular, we can understand that within this gapless regime, the value of G is positive. Okay, and then as the system undergoes this phase transition, okay, so in the vicinity of this critical point of 0.241, G vanishes and then changes sign. Okay. Okay. So now let me kind of ask, how do we expect the dynamical susceptibility or the dynamical correlation to look for such a system in presence of a magnetic field? So I'd like to now add a Zeeman coupling, which is basically just acting as a chemical potential for these two bands. Okay, splitting these two bands by an energy scale which is equal to B. Okay. Now, if I'm thinking of the non-interacting limit, right? So I'm just thinking of this free fermions now, which are the spinons, and asking how will the dynamical correlations look. So I basically need to understand what is the energy cost of single spin flips, and recall that the spin flip is just kind of taking a spin up spinon and turning it into a spin down one. Okay, and so such an excitation at an energy momentum equal to 0 is just equal to this to the Zeeman energy, as you can see here. And as you go to finite momenta, you can see that you expect to obtain these two linearly dispersing branches in the response. Okay, so now we can we basically want to understand how will this dynamical correlations look also away from the non-interacting limit. Okay, and one could speculate that since in this gapless regime G, the interaction strength G basically flows to 0, then you kind of expect this picture to hold throughout this gapless phase. Okay, and this point of view has indeed been taken in a few seminal papers. For example, this one by Yoshikawa and Affleck, where they kind of discuss ESR response of the system and discuss this two linearly dispersing branches. But in fact, if you look at the dynamical correlations numerically, so this was done, for example, exactly at the integrable point using the beta ansatz by Masanori Kono, you can see that when you're looking at this transverse correlations, you can see that there is actually a gap between these two branches, and this gap is also increasing with the magnetization of the chain. Okay. So clearly the interactions are playing a role, and the non-interacting picture is not valid. And it's actually pretty clear to understand why. So the main idea is that while we know that this interaction strength G flows to 0 at very low energies, when we're probing the dynamical correlations at an energy scale equal to the Zeeman energy, the interaction strengths at that energy scale is still finite. Okay, and so we expect this gap that we see to be related to that interaction strength. Okay, but now we basically want to understand the effect of this marginally irrelevant interaction a bit better, and also away from this integrable limit with J2 equals 0. Okay, so one can kind of do some kind of analytic treatment using an RPA approximation and obtain the response in the vicinity of 0 momentum. Okay, and so I won't go into the details of that, but what we find is that one expects to indeed see these two branches. So the dashed lines here, so you can see this two branches of excitations here on the left. And the dashed lines here are corresponding to the non-interacting limit. So in that case, we see two linearly dispersing branches as we expected before. But then once G becomes finite, we see we expect a gap to open up between them, which is proportional to the interaction strength G times the magnetization of the chain. Okay. So this treatment is approximate. And of course, in the case of one-dimensional systems, it's very easy to test this analysis using essentially exact numerics. Okay. So here we're calculating the dynamical susceptibility numerically. Yeah, so as I mentioned before, this is just the Fourier transform on the spin-spin correlations. And here to perform the time evolution, we just employ standard TBD methods. And here we see that indeed, as we tune J2 over J1, okay, so we can basically go to the vicinity of the point where the interaction strength changes sign and vanishes. Okay, and at that point we expect to obtain this non-interacting result, and this is indeed what we see. So here you can see this two linearly dispersing branches originating in an energy which is equal to the Zeeman energy. While as we go away from this non-interacting point, okay, so for example, for J2 equals 0, we need very clearly see a gap opening up. So we can now test that the magnitude of this gap is indeed related to the interaction strengths. And to do that, we kind of continuously vary J2 between away from the non-interacting limit to a finite value of G. And by extracting the magnitude of the gap as function of the magnetization of the chain, we can effectively extract this coupling G. Okay, and so what we observe is that indeed the interaction strength, as we expect, is finite for J to equal 0, for example, and then approaches 0 monotonically as we approach the critical point. Okay? So this is kind of validating the analysis and signaling that we can indeed see signatures between signatures of interactions between these fractionalized spinons in a quantity which can be obtained experimentally. So far I've discussed the kind of low magnetization regime where the excitations are these fractionalized spinons. Of course, when we go to the large magnetization regime, we expect this kind of low energy picture to fail, to break down. And in particular, we see that as we increase the magnetic field now, so staying in the vicinity of this kind of point of the phase transition where the interaction strength between the spinons vanishes, we see that as we increase the magnetic field, the structure of the dynamical correlation changes, and in particular, there is kind of a gap opening up here again between those two branches. So we kind of now want to understand the nature of these two branches in the large magnetization regime. Okay. So to do that, it is useful here to employ a mapping of the spins to just spinless fermions. So this is done by mapping flipped spins to occupied sites on the chain. And when we do that, we basically obtain an Hamiltonian. So I will consider just the kind of nearest neighbor interaction chain first, but allow for some anisotropy in the interactions. So I'll single out this JZ, which is the longitudinal part of the interactions. So in this case, we, of course, see that you basically obtain Hamiltonian, which corresponds to just single fermions hopping in a chain with a cosine dispersion. And then JZ sets the interaction strengths, the density interaction strengths between the spinless fermions. So to understand what this interaction does, we can kind of try and analyze the dynamical correlations starting from the fully polarized state. Okay, so here we kind of go to the magnetic field in which the system is fully polarized. Okay, the magnetization is equal to the saturation value. And in that case, we indeed observe that just a single magnon dispersion in the response. Now, reducing the magnetization a bit, we see that there are two things happening. One is that this low energy branch is splitting, and then there is this higher energy branch showing up. Now, it's useful to consider what happens when we basically turn off these interactions. So we set JZ to 0, and then we see that while the the structure of the lower energy branch remains pretty similar, this high energy branch completely disappears. So we understand that this has to be just the effect of interactions. Okay, so to understand what can interactions do in this case, it's actually useful to consider what happens if we just have two magnons. So in that case, in the system, so we can think of kind of starting from a fully polarized state and then introducing two flipped spins. Okay, and we can write an effective wave function and derive an effective Schrodinger equation for this two-magnon state. Okay. Now, due to translation variance, we can write this state in the following way, where this large K is just the center of mass momentum of these two magnons. Yeah. So solving this Schrodinger equation, we obtain the following spectrum. So here you can see this light blue region is just the two-magnon continuum. But above it, we see that there is a separated state showing up, and we can check that this state is actually a bound state of two magnons. Okay, so we can look at the spatial structure of this wave function, and we see that it's a bound state of these two magnons. Now, why would we expect this state kind of to show up in the dynamical correlations? So to understand that, we can think of the very large magnetization regime, basically when we have just a single flipped spin in the ground state. So now, probing the dynamical response, we're basically flipping another spin. And now we understand that this state can have an overlap with the two-magnon bound state. Okay. Note, however, that since the kind of the minimum of the single magnet dispersions is at momentum pi, the two-magnon bound state that will probe when we flip a spin with momentum k will be at momentum pi plus k. Okay. So now we can again kind of test this numerically, so here you can see the dynamical correlations again, and in the inset you can see this kind of high energy region on a slightly different color scale. And the red dashed line is the energy of the two-magnon bound state at momentum pi plus k. So you can see that this high energy feature agrees exactly with the energy of the two-magnon bound state at pi plus k. And this is, of course, kind of not relying at all on the integrability of the model. So if we go to finite J2, we can repeat a similar analysis and see that this high energy feature is again appearing at energies at which we expect to see the two-magnon bound state. Okay, so let me now just briefly discuss the case of higher dimensional systems. So basically, I'd like to argue that the appearance of this two-magnon bound states in kind of the simple scenario of very simple antiferromagnets is actually generic to two-dimensional systems as well. Okay. So performing kind of similar analysis, and for simplicity, just considering the simplest system of a square lattice antiferromagnet in a Zeeman field, we can again just derive an effective two-magnon Schrodinger equation above for a fully polarized state, introducing just these two magnons, and we again find that that the spectrum looks in the following way. So this light blue region is just the two-magnon continuum, but now again, in addition to the continuum, we see two well-separated states, which are bound states of the system. Okay. Now, the analysis in this case is actually slightly more subtle, because we know that once we have once the state is not fully polarized, but we go somewhat below the saturation field, there's actually condensation of magnons, so there is a long-range order forming in the system, and the spins are now kind of slightly or canted out of the plane, but the transverse component features a long-range order. But now carrying kind of performing a standard analysis of using a kind of Holstein-Primakov transformation and thinking of the spins as bosons. So within the just linear spin wave theory, allows us to obtain the dispersion of these magnons. But now going into higher orders in using the Holstein-Primakov expansion, we can understand what we can kind of obtain the interaction terms within these magnons, and performing a projection onto this two-magnon subspace, and understanding what do the magnons, what would the interactions between the magnons do. We actually again find that within this projection, we expect to see these two-magnon bound states appearing also when the field is below the saturation. So again, to probe this, to understand whether this picture is correct, we can try and probe this numerically. So of course, in the two-dimensional case, the analysis is a bit more subtle, but we can basically employ similar methods, but now on kind of finite circumference cylinders. Okay. In this case, to perform the time evolution of the system, we use an MPO representation of the time evolution operator, and kind of looking at finite circumference cylinders, it basically allows us to probe the dynamical correlations at various cuts in the Brillouin zone. And so which cuts exactly would also depend on the boundary conditions that we choose. So
Anna,
just,
sorry to
that's not the last slide. Almost.
Okay, good.
Yeah.
Yeah, okay, good.
Okay, yeah, so I'll just flash kind of the results that we obtain for the square lattice system. So this is for cylinders of width 6, and this is kind of using the standard boundary conditions and probing the response along a cut in the Brillouin zone, which is at ky = 0. So you can see that this is the response we get. You can see here the single magnon branch, which is the higher intensity branch, but there's also this upper branch appearing, and we can try and compare the energy of this branch with the energy that we expect for the two-magnon bound state, and we can see a pretty good agreement. Now we can also kind of probe different geometries, right? So these boundary conditions allow us to probe a different cut along the Brillouin zone, passing through the gamma point. And here again, you can see the single magnon branch, but also this higher energy branch appearing. And again, it compares pretty well to the energies of the two-magnon bound state. Okay, so just to summarize, I wanted to show that using kind of probing the dynamical correlations, the dynamical field correlations numerically, we can identify clear signatures of interactions between quasiparticles, both in one-dimensional systems and also in higher dimensional systems. So of course, for the higher dimensional case, there's still a lot of open questions. And in particular, we need to understand this kind of the scaling of the intensity of this higher energy branch over the system size to make sure that this is not an effect coming from the quasi 1D nature of the system. And also understand better the evolution of this bound state with the magnetization of the system. And of course, the fact that we are using matrix product state-based methods would allow us to probe the behavior of this bound state also on other lattices, which might be more frustrated. Thank you.